Good morning, ladies and gentlemen. This is Charlie Liu. No, actually, no, I'm not. I'm not Charlie Liu. I'm just a substitute of him because he doesn't want to show up on a camera. So, this lecture, we're going to focus on the physics concept of ideal gas law. Does anyone know what's an ideal gas?
Oh, mister, is an ideal gas a gas that is in the ideal condition?
No, boy, you're saying nothing. Since nobody knows what's an ideal gas, I'm gonna talk about it. So now, open your physics textbook. There are 6 assumptions to an ideal gas. Listen, first one, the particle of a gas, the atoms or molecules obey Newton's laws of motion, but gravitational effects can be ignored. Secondly, the volume of the individual gas particle is very small compared to the volume of the gas or the volume the gas occupies, which is common sense, and the collision between the particles and the walls of the container and between the particle per se is elastic, which means there will be no kinetic energy loss. And second, lastly, there are no force between the particle, which means the internal energy of the gas is only the kinetic energy. Lastly, the duration of collision is really small compared to the time between each collision. And okay, now, after knowing what's an ideal gas law, let's do a fun little experiment right now. So imagine, actually, there's no need for imagine. There is a plastic bag with a volume of gas in it. What will happen if we just push the bag? Okay, let's try. Now I'm exerting a large force onto the bag. Thus, from the experiment of this plastic bag right here, we can see that as a large force exerts onto this plastic bag, it explodes. Simply explode. But why does this happen? Anyone know? Okay, then I'll explain it. So, as a force exerts to the bag, like this, the force will push the bag, and hence reducing the volume of it. And as the volume is reduced, the particle will collide with the wall of the container, which is the bag, more frequently. And such frequency will increase the pressure of the bag, or the pressure inside the bag. And as the volume keeps decreasing, the pressure keeps rising. And at one point, when the pressure is too high, the bag, which is made of plastic, which is not a really strong material, finally breaks apart like this. Conclusion we can draw from the experiment is that as volume of the bag decreases, the pressure of the air increases, and this inversely proportional relationship between the factors can be expressed as P equals to a constant K times 1 over V. And there's actually other way to torture the bag. For example, if we want the sealed bag to explode, we can just put the bag above a burning fire. With the increasing temperature, the pressure will increase as well, and soon the material will not stand high pressure and will explode. Why does increased temperature leads to an increase in pressure? Let's see in the simulation. Since it is a fixed volume, we can just lock up the piston. So let's lock up the piston. And now take notice of the pressure right here. And I will now heat the gas inside the volume of container. And as I heat it, the pressure of the gas will increase proportionally, as you can see, and that's actually reasonable. And because, as can be seen in the graphic simulation, the particles actually move faster as temperature increases, which is reasonable because as temperature is the measure of the average kinetic energy, and therefore as temperature increases, the kinetic energy of the particles increases as well, and they will move faster, and they will collide with the container of the wall of the container more frequently, which will exert a higher pressure to the walls of the container. And therefore, this proportional relationship exists because as temperature increases, the pressure will increase proportionally as well. And this can be expressed as P equals to constant K times T. There's actually more of this relationship. For example, a proportional relationship also exists between temperature and volume. And as can be seen in the simulation, we can just first cool the temperature for a bit. And now, let's unlock the volume and notice whether the pressure will still change as we increase the temperature when the volume is unlocked. So now, as I heat the temperature, the pressure does not change at all. The only thing that changes is the place of the piston and the volume of the gas. And as the temperature increases, the volume increases as well. And therefore, a proportional relationship is generated where V equals to T times a constant K. And another proportional relationship we can generate in terms of the gases is that V is proportional to the moles of the gas. And that's reasonable because for ideal gas, 1 mole of gas actually takes same volume. Therefore, the volume of the gas have a proportional relationship with the mole, because if 1 mole of oxygen in STP takes 22.7 liters of volume, 2 of them just simply take 45.4 liters of volume. Thus, the proportional relationship can be expressed as volume equals to K times N. And now, if we combine the three, V is proportional to 1 over P, and V is proportional to T, the temperature, and V is also proportional to the number of moles in the gas. And now we just combine them, and they can just give V is proportional to T times number of moles over P. And we move P to the other side, it gives PV is proportional to Tn, and we can express this proportional relationship to an equation by adding a constant n, or a ratio n, where PV equals to K times Tn. And from scientific research and experimentation, the scientists figured that the constants, which is gas constant, and the K is determined to be R, which is 8.31 in this case. And the ideal gas law is hence formed or derived at PV equals to nRT. The ideal gas law is a fairly important physics concept and chemistry concept because it has a really wide application. It is commonly used to derive the unknown factor by using the known factor. For example, if I know the pressure of the gas, the volume of the gas, and the temperature of the gas, then by using the ideal gas law, I am enabled to calculate the number of moles of the gas. And when it's applied in the real circumstances, it will not be absolutely accurate, because this equation applies to ideal gas, and ideal is definitely different from the real gas, although they behave similarly in room temperature and room pressure. And okay, guys, thank you for listening. Be realistic. See you sometime.